So far, section 6.6 has been pretty easy, but I would anticipate that if you get a question from this section, it'll probably be a word question, and it won't be quite as easy as we've seen so far. So we're going to do example 5 here to give you a little bit of experience with a bit more difficult problem. We've got a cone tank, and in it we have olive oil. Okay, and we want to find out how much work would it take to pump the olive oil out of this tank. And the tank is 10 feet tall, and the level of the olive oil currently is at the 8-foot level. We want to drain the tank, and the diameter at the tank, this is the y-axis here, the diameter of the tank is given by x, the radius, excuse me, let's make this the radius. I think this is the radius. Yeah, the radius is equal to 1/2 y. So maybe I won't say x, I'll just say r. The radius at any point is just 1/2 y. So now we can imagine a disk, just like in our solids of revolution. We can imagine a disk, and it's got a little teeny infinitesimal thickness that I have overrepresented here, but we can imagine it, and it's in the dy direction, and we ask, well, what is the volume of that one little disk? Well, it would be dy times pi r squared, and this is 1/2 y, oh, I saved it, squared, and 1/2 squared is 1/4, so we get 1/4 pi y squared dy, and the dy is our representation of this infinitesimally narrow thickness. Okay, so that's the volume of our little hypothetical disk, but we're not actually interested in volume. We're interested in what is the mass of this little puppy, and we've got to multiply its volume times its density, and that's given in the problem that the density is 57 pounds per cubic foot, like that. So we have to multiply 57 times this. When we do that, we get how much mass we have to pump out of here. So let me write this out. This is 57 times 1/4 pi y squared dy. So far so good. But now, how far do we have to actually pump this oil out, given that we're sitting right here? Well, we have to pump it up and over the lip here, up to the 10-foot level. But we don't have to pump this oil all the way from the bottom, so not the full 10 feet. It's from wherever we are, and we're sitting at y, and so we want just this distance, and that's going to be 10 minus y. Okay, so if we put it all together to deal with this little thing here, we've got 57 times 1/4 pi y squared, and we might as well include this term now, 10 minus y dy. And of course, you can guess from calculus that what we're going to now do is just say, yeah, but now let's just integrate over 0 to 8 for all the little hypothetical disk from 0 to the top of the fluid, which is at 8. And then this will give us the amount of work done. Okay, so we're ready to do our integration. Let's just clean this up a little bit. What can come out? Well, 57 pi divided by 4. Certainly we don't need that in there. Integrate it from 0 to 8. Now we probably should go ahead and distribute, make this 10y squared minus y cubed dy, something like that. And when we integrate this, we're going to just get 57 pi divided by 4. This would become 10y cubed divided by 3. Better put a bracket in there. Minus y to the 4th divided by 4. And we're going to evaluate this from 0 to 8. You plug in your values using a calculator and you get something like 30,561 foot-pounds. And that's the answer. I'll just go back up here for 1 second. I got to thinking about this, and note that, you know, when we calculate the mass of this oil, the force needed to lift the mass is equal to the mass. It counterbalances the force of gravity. So if this weighs 10 pounds, it takes a 10-pound force to raise it. And that's why when we came up with this weight, volume times mass, volume times density, the 57 pounds per cubic foot, that gave us a measurement of force. Hope that's clear.